The laws governing the world of classical dimensions in nature have been termed the laws of classical physics. According to these laws, all movements in the classical world can be mathematically predicted, deterministically based on Newtonian mechanics. Since humans are also objects in classical dimensions, the martial arts performed by humans are also governed by these classical laws. Before exploring the science of this art, let's learn about the physical quantities of an object in linear motion in the classical world, and then apply what we've learned to a linear punch. An object moving at a constant speed in one direction possesses physical properties such as velocity and mass. The resistance of an object to changes in its velocity is known as mass. Think about it. While it's difficult to change the velocity of a heavy object, it's easier to change the velocity of a lighter object. You might think this is due to frictional forces, but even in a frictionless environment like space, it's harder to move a heavier object. Therefore, mass and velocity are inseparable and integral components of physical reality. From the combination of these two properties, linear momentum emerges. Due to this momentum, the object possesses an energy value known as kinetic energy. When observing the classical world, Newton discovered that a linear force must be applied to give velocity to a stationary object. He defined force as the rate of change of momentum with respect to time and experimentally verified this in the classical world. When this force is applied to the object throughout its motion, it transfers energy to the object, which can be calculated using integration. From this, the energy transferred by the force to the object consists of the change in its mass plus the change in the square of its velocity. Currently, we are not examining systems like rockets that gain movement by losing mass. After all, who uses rocket fuel to throw a punch? In the system we are studying, the force changes velocity, so we can reasonably conclude that the energy arises solely from the square of the object's velocity. When an object in linear motion collides with another object, its speed decreases over a certain period. Consequently, its momentum and energy will also change, and if this energy is transferred to the other object in the forms of kinetic energy, heat, and sound, the collision is called an inelastic collision. If all of the kinetic energy is transferred during the collision, it is referred to as an elastic collision. After a collision, objects transfer their energy to the impacted object over a certain period. However, the intensity of the effect they exert depends on how quickly this energy is transferred. I'm not saying this because of some divine revelation. It's because if the same amount of energy is transferred over a longer period, the force applied per unit of time decreases. This results in less force being exerted, which means a less intense effect. In physics, the quantity that represents intensity is called power, and it is calculated as energy transfer divided by the transfer time. This equation fully reveals the mysteries of collisions. Looking at it, we can see that collision time and momentum change have a significant impact on the intensity of the collision. Let's examine the importance of these physical properties with two examples. Suppose an object is moving with a velocity v. It collides with another object and comes to rest after 2 seconds. The resulting collision intensity will be v²/2. Now imagine another object, also moving at velocity v. This object, upon collision, rebounds, thereby shortening the collision time to 0.2 seconds. In this case, the collision intensity will be 5 volts, which is 10 times greater than in the first scenario. Let's keep this crucial effect in mind. It will come in handy when analyzing how to throw punches. Momentum is a quantity that incorporates mass, and mass also influences the energy that an object gains due to its velocity. Therefore, mass also affects the intensity of the collision. To illustrate this effect, let's examine objects of different masses, each colliding at the same velocity v/1 second. Suppose the mass of the first object is 10 kilograms. This object, moving at velocity v, collides with another object for 1 second and comes to a stop. The collision intensity in this case will be 5v². Now, let the mass of the second object be 30 kilograms. This object also moves at velocity v, collides for 1 second, and comes to a stop. Here, the collision intensity will be 15v². Let's also keep this effect in mind. It will be crucial when analyzing the role of arm weight in punching. Let's stop imagining our linear moving object as a punch and return to real-world applications. Based on what we've discussed, the mass, speed, collision duration, energy, and momentum of a punch are all factors that influence the impact it leaves. Since we are only examining the physics of linear motion, we'll focus on the linear moving punch known as the straight punch. The straight punch is one of the shortest and most effective attack techniques used in boxing and martial arts. Delivering this punch correctly and effectively involves following specific steps. First, the feet are positioned shoulder-width apart, with one in front and the other behind, a stance whose physics we will understand when we hunt it. The knees are slightly bent to provide balance, and body weight is evenly distributed across both legs. Fists are kept at chin level, with elbows close to the body, allowing energy to be transferred over a longer distance in greater amounts. The movement starts from the shoulder, pushing forward, with the elbow moving in a straight line at shoulder level, thus imparting momentum to the punch. While the punch moves, the wrist is kept straight, and the knuckles of the fist are aligned perpendicular to the target. The power of the punch comes not only from the arm, but also from the rotation of the hips and shoulders, which increases the contribution from this rotational energy. However, we will learn about this effect of rotational power on the punch in the next video. By rising onto the toes of the back foot, the hips and shoulders are rotated forward, adding extra momentum to the punch. As the punch approaches the target, the hand is fully clenched, and the joints are locked while keeping the wrist aligned in a straight line. This is important to prevent damage from the reaction force upon impact. When the punch makes contact with the target, the elbow is fully extended and the impact is delivered through the first two knuckles of the fist. Immediately after contact, the punch is swiftly retracted to the starting position, the elbow is brought back close to the body, and the defensive stance is maintained. When these steps are executed correctly, a straight punch achieves maximum efficiency in terms of both speed and power, delivering an effective blow to the opponent. As you can see, the intensity of this motion depends entirely on the factors we just examined. Now that we've learned how to throw a punch, let's delve into how mass and momentum are influenced by muscles. First, let's observe the case of a person with an average muscle mass throwing a straight punch. We can assume that the muscle mass in the arm of this person is approximately 2 kilograms. The speed of a punch delivered by 2 kilograms of muscle is about 10 meters per second. If we assume the collision duration is 2 seconds, the intensity of the punch can be calculated as 100 joules per second, based on what we've previously learned. According to Newton's law of action and reaction, this force will also act back on the punch. That's why posture is crucial when punching, and we'll examine this topic in detail in future videos about the science behind martial arts. Does having more muscle always mean winning a punching contest against someone with average muscle mass? Of course not. At the outset, we noted that momentum is formed by the inseparable pair of mass and velocity, and that mass resists changes in velocity. This applies here as well. Increasing the speed of a very muscular arm means facing greater resistance, which requires more energy. This is influenced by many factors. Let's take a closer look at how the muscles responsible for punching perform this function. The muscles in our arms consist of fibers, much like a rope. These fibers contract when stimulated by calcium ions after receiving signals from the brain, enabling our arms to move. The more fibers there are, the greater the tension and the more force produced. However, if these fibers do not contract synchronously, the force generated will be uneven, leading to inefficient energy use. Synchronization can be improved through training. However, more fibers also mean more mass, and as mass increases, resistance to acceleration grows. Thus, the relationship between muscle mass and speed has a maximum value unique to each individual. This is the muscle mass that maximizes the punch's intensity or momentum. Therefore, someone with excessive muscle mass cannot outperform someone with sufficient muscle mass in a punching contest. We analyzed the straight punch within a scientific framework. In our example, we assumed a collision duration of 2 seconds, which we learned affects the intensity of the punch. Based on this, we can identify the key point for an effective straight punch. Not just for a straight punch, but for all punches, you should pull your fist back immediately upon contact with the target. This reduces the collision duration, thereby increasing the intensity of the punch. Pulling your fist back has additional benefits beyond increasing punch intensity. Your fist quickly returns to a defensive position, and your opponent finds it harder to predict the location of your fist. The straight punch doesn't have to rely solely on energy from linear momentum. There are additional techniques to enhance this punch, but these will be examined after we hunt science of rotational motion. In the next video, we'll incorporate rotational movement into the equation, aiming to throw a punch that maximizes power by utilizing our entire body through rotation. So stay tuned. For now, good luck with punches using linear force.